In this video, I'll talk about solving trigonometric equations. So in particular, we're going to be looking at a specific kind of equation. The general topic of solving equations involving trigonometric functions is a big one. So I'm going to focus on just looking at equations that have the form trig function of x equals a value. There are more complicated trigonometric equations, but many of them can be reduced to that form. So that's a really important case for us to consider. And so within that case, we're going to be looking at two important subcases, which are using reference angles and special angles to find exact answers, and then also using the calculator, but understanding how to interpret and use the answer that the calculator gives us. So for our first example, let's just look at sine of x equals 1/2. So this means that we're looking for all values of x, all angles, whose sine is 1/2. So when we initially start thinking about this, there should be one angle that immediately comes to mind. We know that the sine of pi over 6, 30 degrees, is 1/2. So certainly x equals pi over 6 is a solution to this problem. But it's clearly not the only solution. So if we look at our unit circle, remember that on the unit circle, when we have an angle, in this case pi over 6, the point that corresponds to that angle on the unit circle, the y-coordinate is the sine of that angle. So in this case, that point has y-coordinate 1/2. But it's not the only point on the unit circle that has y-coordinate 1/2. Over here in quadrant 2, we've got another point that also has y-coordinate 1/2. What angle does that correspond to? Well, the reference angle for that angle is also pi over 6. Remember, that's how reference angles work. So this angle here has to be the entire half turn pi minus the pi over 6, because I don't complete that half turn. I stop pi over 6 short of a half turn, and so that gives me 5 pi over 6. So that's another solution to my equation, x equals 5 pi over 6. But even that's not a complete solution, because we know that the trigonometric functions are periodic. So for example, another solution to this equation would be to complete a full rotation around my circle and then go an additional pi over 6. Or I could complete 3 complete rotations, 2, 3, and then go to my pi over 6. So in fact, any of these solutions, if I add any integer multiple of 2 pi, that is going to give me yet another solution. So the way that we're going to write that is we're going to say plus 2k pi to each of these solutions, and we'll say where k is an integer. Because of course we could also subtract 2 pi or subtract any integer multiple of 2 pi and get another solution. So that's the complete general solution to this equation. It has infinitely many solutions, but they all either look like pi over 6 plus some multiple of 2 pi, or they look like 5 pi over 6 plus some multiple of 2 pi. Let's do another example. So this time we've got the tangent of x equals negative square root of 3. So this is a little bit more complicated because of the minus sign, but again, we should know that the tangent of a particular special angle is the square root of 3 without the negative sign. And that angle that we're thinking of is pi over 3, 60 degrees. So again, let's think about how we can use that information on our unit circle. So again, remembering the device that we have for remembering which trig functions are positive or negative in each quadrant, we have ASTC, and this means that tangent is negative in quadrant 2 or in quadrant 4. So the angle we're looking for either lives in quadrant 2 or quadrant 4 because the angle we're looking for has a negative tangent. The other thing we know about this angle is that its reference angle is pi over 3. So the reference angle for the x that we want is pi over 3. So that gets us a sketch of where this angle lives on that unit circle. We've got an angle over here in quadrant 2 whose reference angle is pi over 3. And we've got an angle down here in quadrant 4 whose reference angle is pi over 3. So that gives us this angle here, which is similar to the one that we just did, pi minus pi over 3, which is going to be 2 pi over 3. And then we've got this angle here, which is a complete rotation minus pi over 3. So that'll be 2 pi minus pi over 3, which is 5 pi over 3. But as usual, we can add any multiple or subtract any multiple of 2 pi to get additional solutions. Now, one of the things that we talked about the tangent function in particular, tangent and cotangent both had this property, that the periods of those functions is actually just pi. So one way that we could write our solution is similar to what we just did in the previous problem. 2 pi over 3 plus 2k pi, 5 pi over 3 plus 2k pi, where k is any integer. But there's actually a more compact way that we can write that, and that's simply to say x equals 2 pi over 3 plus k pi for any integer k. And that's because the period of the tangent function is just pi. And in fact, 5 pi over 3 is 2 pi over 3 plus 1 pi. So that's the more compact way to write it. So that would be what we would prefer, but this answer that we wrote down first is also correct. All right, now what if the angle that we're looking for is not involved with a special angle? So this problem is a little bit different in a couple ways. One is that we're trying to solve sine of x equals negative 3/4, and we don't know any special angles that have a sine value of 3/4. So this is going to be a problem that we're going to solve using the calculator. The other thing that we're given is that we want to solve the equation on the interval 0 to 2 pi. So that means that we're not going to necessarily have infinitely many solutions because we're restricting where the values can live. So we're only going to be looking at answers between 0 and 2 pi, so we're not going to have the plus 2k pi like we did in the previous problems. So one solution that will pop out immediately is to simply take the inverse sine of both sides. The inverse sine of the sine of x is going to equal the inverse sine of negative 3/4, and that's going to give us a value from our calculator of x equals negative 0.848062. And there's more decimal places, but I'll just stop there. Okay, what we know about the inverse sine function is that the values that we get out of the inverse sine function always lie between negative pi over 2 and pi over 2. That was part of what we did when we defined the inverse sine function, was we restricted the sine domain to be negative pi over 2 to pi over 2. So this weird value, negative 0.848, is between negative pi over 2 and pi over 2. And oh, by the way, if you're following along with this on your own calculator and you didn't get negative 0.848, that's probably because your calculator is not in radian mode. And as always, when we're thinking of these trigonometric and inverse trigonometric functions, we always want our calculator in radian mode. So go ahead and change that mode to radian mode, and you should get the same answer that I'm getting here. So where does this angle live? Well, it's between negative pi over 2 and pi over 2, and it's negative, so that means it's got to be in quadrant 4. So the angle down here of negative 0.848062 radians is this angle. Now, unfortunately, that angle does not lie between 0 and 2 pi. It's negative. So what is the actual angle between 0 and 2 pi that matches with that location on the unit circle? Well, that's going to be this rotation, which will be 2 pi minus 0.848062. So this rotation here, 2 pi minus 0.848062, that works out to be 5.435123. And that's one of the solutions that lies between 0 and 2 pi. Are there any other solutions? Well, again, remember, on our unit circle, the y-coordinate on the unit circle is the sine value. So where is there another point on my unit circle with the same y value? Well, that's going to be over here in quadrant 3. There's another mirror point that also has a y-coordinate of negative 3/4. The reference angle for that angle is again going to be this 0.848062. So this angle here is 0.848062. And then the angle that we're looking for is going to be pi plus that reference angle. So this angle will be pi plus 0.848062, and that works out to be 3.989655. So those are our two solutions to this equation that we're trying to solve. Again, we're using reference angles, but we're getting the reference angle from the calculator this time rather than from our knowledge of special angles. Okay, let's do one more. So we're being asked to solve cosine of x equals negative 0.36. Again, we're going to start by using the calculator to get x equals the inverse cosine of negative 0.36, and that's going to give us x equals 1.939064. And again, we have to remember that by the definition of inverse cosine, this angle is between 0 and pi. Okay, so what quadrant does 1.939064 lie? Well, again, we have to be a little bit of a detective here. We know that cosine is negative in quadrant 2. This angle is either in quadrant 1 or quadrant 2. This angle has a negative cosine, so it must be in quadrant 2. So the angle that we're starting with, the angle that our calculator is giving us, is this angle right here. That's going to be our 1.939064. But is that the only result? Well, no. Again, on our unit circle, this time because we're talking about cosine, cosine is the x-coordinate of this point. And so is there another point that has that same x-coordinate? The answer is yes, and it's down here in quadrant 3, the same x-coordinate, negative 0.36. So now our question is, what is this angle? Well, we don't actually yet know the reference angle, and if we can figure out the reference angle, then we'll be able to figure this out. So the reference angle of the original solution, 1.939, is this angle in here. So that angle is a half turn minus the angle that we found, 1.939064, and that works out to be 1.202528. So that reference angle is the same reference angle as down here, so that's also going to be 1.202528. And so the angle that we're looking for is going to be pi plus that 1.202528 reference angle. And that works out to be 4.344121. So we've got two solutions between 0 and 2 pi. Those two solutions are 1.939064, that's the one we got from the calculator, and we've also got 4.344121, that's the solution that we just figured out using reference angles. Now this one did not have a restriction on where the solutions could live, so we're back to needing to put plus 2k pi, and again where k is any integer. And that would be our solution to this equation. The nice thing about this is you can actually go back and check your answer. So if you take, for example, on your calculator, the cosine of 4.344121, you will get pretty close to negative 0.36. So it's a nice way when you're using reference angles to get additional solutions to go back and use your calculator to check those solutions to make sure you're actually getting the trig function value that you think you're supposed to get. Okay, so what did we do in this video? We did a lot of examples. We learned how to solve that particular kind of trigonometric equation where it's a trigonometric function of x equals a value. And again, that's not every trigonometric equation, but most other equations involving trigonometric functions can be boiled down to something that looks like that. So knowing how to solve these kinds of equations is going to get you pretty far. And the next time, we're going to go back and try to develop some more trigonometric identities, and these will be a whole bunch of different identities, including formulas for sine and cosine of the sum and difference of two angles.